We are going to introduce our work, improving point-based crowd counting and localization based on auxiliary point guidance. Crowd counting and localization aims to identify and count individuals within crowds. Existing crowd counting methods fall into three categories: map-based, detection-based, and point-based. In this paper, we aim to improve the existing point-based method. Point-based crowd counting consists of three main steps: point proposal prediction, proposal target matching, and loss calculation. First, the model generates point proposals from feature maps, using two branches for regression and classification. Each pixel corresponds to an image patch, predicting offsets and confidence scores for point proposals. Next, the Hungarian algorithm matches each ground truth point with a proposal based on distance and confidence. Matched proposals are positives, unmatched ones are negatives, ensuring accurate localization. Finally, the model computes the loss, combining Euclidean loss for regression and cross-entropy loss for classification. We examine if each ground truth consistently matches the same proposal across different epochs during training. Here, we introduce the instability rate, which quantifies the rate of inconsistency in point proposal selection compared to the previous epoch. The blue line represents the existing point-based strategy, showing that over 50% of ground truth points fail to consistently match the same proposal throughout training. This phenomenon could lead to problems, such as lower confidence scores for proposals close to ground truth points. Consequently, during inference, no proposal may be chosen as a positive match for this ground truth. Another issue arises because there is no constraint on the offset value. The matching process only considers the distance of the final position and the confidence score. It could mistakenly treat unrelated proposals as positive matches after applying the offset. In this paper, we address these challenges by introducing auxiliary point guidance, offering explicit guidance throughout the training process. Building on the matched points identified by the existing point-based method, we further introduce auxiliary positive points to guide the network. These positive points are assigned based on the ground truth position, incorporating a small margin of randomness. We then ensure that these points have higher confidence scores, and their positions, after applying the offset, should be close to the ground truth. The rationale behind this operation is the assumption that the matched proposal is usually close to the ground truth point's position due to shared similar spatial features. This operation aims to increase the likelihood that proposals close to the ground truth will be selected as matched points during the matching process. Next, we further introduce k-auxiliary negative points to guide the network. These negative points are assigned based on the position of ground truth with larger margin of randomness. We then ensure that these points have lower confidence scores and minimal offsets. This operation aims to decrease the likelihood that proposals not close to the ground truth are selected as matched points during the matching process. Following the optimization with APG, the matching process will tend to select the nearest proposals with the highest confidence as the matched point. In APG, since auxiliary points are assigned randomly, their features may correspond to arbitrary positions in the image. However, traditional bilinear upsampling methods struggle to accurately capture these features. To address this issue, we introduced the technique of implicit feature interpolation. To extract feature at arbitrary position, we introduced implicit feature interpolation. For a target point, we identify the 4 nearest feature points and their distances to this target. Positional encoding is added to these distances to capture detailed features. The features are processed by a multi-layer perceptron, interpolating the exact feature at the target point. We introduce APGCC, a fusion of VGG encoding and ATRA spatial pyramid pooling for enhanced crowd analysis. It adopts VGG to extract key image features for further processing. Features from the convolution 3 and convolution 4 layers are refined using ATRIS spatial pyramid pooling. Next, we calculate target features precisely through implicit feature interpolation. These features guide the prediction of confidence scores and offsets, pinpointing crowd counts and locations. The model trains on a blend of point-based matching constraints and auxiliary point guidance, minimizing the overall loss. In crowd counting, APGCC consistently ranks first in both mean absolute error and mean square error across numerous benchmarks for average performance. In crowd localization, APGCC demonstrates exceptional performance across various benchmarks. The proposed APG is designed to lower the instability rate during the matching process. As demonstrated in the right figure, compared to the existing point-based strategy, APGCC effectively reduces the instability rate, leading to more accurate counting results. The visualization in the left figure displays the matched proposal for each individual, where dots mark the original positions of proposals and arrows show the offsets. Without APG, some individuals might incorrectly select the background or another individual as the matched proposal, often with a larger offset. In contrast, APGCC accurately selects the appropriate proposal to match each individual. Thank you for your attention. Please read our paper to find out more.